The second method that I want to share with you is called the Simpsons Rule. The idea of the Simpsons Rule is to approximate the curve that connects three consecutive points with a second-order polynomial. The concept of the Simpsons Rule is similar with the trapezoidal rule, in which the interval is divided into multiple segments. While the trapezoidal rule connects two consecutive points to form a linear approximation that subsequently creates a trapezium, the Simpsons rule connects three consecutive points to form a quadratic approximation. So that's why in most cases the Simpsons rule provides more accurate results compared to the trapezoidal rule. So let's see how the Simpsons rule is formulated. For illustration, I use a few number of subintervals . But for this Simpsons rule with quadratic approximation, the number of subintervals must be even because each curve that connects three consecutive points will combine two strips at once, this and this. Sorry. Then the last point in the curve will be reused to create the second curve that covers the next two strips, and so on. So remember that the small n must be even. Before we proceed any further, we need to know what is the equation that represents the curve that connects these 3 points. So suppose that the 3 points are T1, Y1, T2, Y2, and T3, Y3. So using this second-order Lagrange polynomial, the equation for the curve is y equals to t minus t2 times t minus t3 divided by t1 minus t2 times t1 minus t3 times y1 plus, let me copy this term, and one more term. And I'll remove the subscript. Okay, so continue. The first term is this, plus t minus t1 times t minus t3 divided by t2 minus t1 times t2 minus t3 y2 plus t minus t1 times t minus t2 divided by t3 minus t1 times t3 minus t2 times y3. So this is called the second order Lagrange polynomial. So the area of the two strips below this curve, so let's have some space. Again, the area of the two strips below this curve is the integral of t1 until t3 y dt, in which t1 is here, t3 is here, and y is the equation for this blue curve. So, and we need to take this expression to the integral. But before that, it's better to simplify the expression using some substitution technique. Now let's introduce r equals to t minus t1 over h, in which h is b minus a divided by small n. So we can also write t minus t1 equals to hr. So even t minus t2 equals to hr minus h, because the distance between t1 and t2 is h, and we factorize h to have h times r minus 1, and also t minus t3 equals to hr minus 2h equals to hr minus 2. And lastly, the differential elements dt equals to hdr, that can be derived from this equation. Now if we substitute all the factors in the polynomial with h and r, so if I copy this, and then I substitute all the factors in this equation with h and r, so we will have, let me clear this first. Okay, so we will have h r minus 1 times h r minus 2 divided by negative h times negative 2h, because this is t1 minus t2 that equals to negative h, and t1 minus t3 equals to negative 2h, and so on. And then the second term becomes hr times hr minus 2 divided by h times negative h, and the last term is hr times hr minus 1 divided by 2h times h. And each numerator and denominator consists of h squared term. If you can see here, h times h squared, even at the denominator, so they can be cancelled out from the equations. And finally, the equation becomes this equals to r minus 1 times r minus 2 over 2 times y1 plus minus r times r minus 2 y2 plus r minus 1 over 2 y3. So the integral becomes, I need more space down here. Okay, so the integral t1 until t3 y dt, which compute the area below this curve, equals to the integral of this expression I think I have to change it to blue. Okay, so the integral of this expression dt, in which dt equals to h dr, and when t equals to t1, if t equals to t1, we get r equals to 0. If t equals to t3, r equals to 2. So the limit of the integral becomes from 0 to 2. And I hope you can prove that this integral equals to h over 3 y1 plus 4y2 plus y3. So again, this expression is the area of the two consecutive strips, this and this. So if we have 6 strips like this, so we can take this formula. Let me adjust this a little bit. Sorry. So if we have 6 strips, we can have this formula for the total area below graph, h over 3 y1 plus 4y2 plus y3, in which this is y1, y2, y3, and then y4, 5, y6, 7, 8, and 9, plus h over 3 y3 plus 4y4 plus y5, and plus h over 3 y5 plus 4y6 plus y7. So the first term in the expression represent the area of the and I think I need one more, h over 3 y7 plus 4y8 plus y9. Alright, so the first term in the expression represents the area of the green area, and then the second term refers to the red area, the third term represents the area of the blue, and the last one represents the area of the yellow area. So if you notice, the terms y3, y5, and y7 appear twice. And then the term y2, y4, y6, and y8, they appeared once but multiplied by 4. And lastly, the term y1 and y9 only appear once. So if we rearrange them, we can have this equals to h over 3 y1 plus 4 y2 plus y4 plus y6 plus y8, and plus 2 times y3 plus y5 plus y7, and plus y9. So if we had n data points, so we can modify this equation to become, sorry, one more try. So again, if we have n data points, so we can modify this expression to become plus until y big N minus 1, and then plus again until y big N minus 2, and finally plus yn. Okay, so this continue down here. Or using the summation notation, we can write this term equals to h over 3 y1 plus 4 the sum of I from 2 until n minus 1 yi plus the sum of I from 3 until n minus 2 yi plus yn, but the condition for the summation, so this one I must be even and another one I must be odd. And also by substituting h equals to b minus a divided by n, so we can show that finally these terms equals to, again, if we substitute h equals to b minus a over n, we can show that this equals to b minus a times this expression divided by 3n. And similarly, like we did in the trapezoidal rule, this can be interpreted as the width of the area times the average height. Okay, and finally we can show that the formula for the average value, the RMS value, and the power using the Simpsons rule as the average value is 1 over 3n so I change this to f. Okay, so this is the formula for the average value. And then for the RMS value, using the similar manner that we did in the trapezoidal rule, the RMS value equals to this term, but f has the square, and then we take the square root of the overall term. And lastly, the normalized power is equals to the RMS expression without having the square roots. I think constant 2 was missing from the expressions. Yeah. Sorry because I forgot this times 2 before the summation of the odd number, because as I mentioned to you, y3, 5, 7 and so on, they appear twice in the expression. So this should be multiplied with 2 and this one as well, and all of them. The summation for the odd what you call data points should be multiplied with 2 except f1 and the final data. Alright, so to summarize this video lesson, we have derived 2 sets of formula for computing the average value, RMS value, and the power, in which the first formula was using the trapezoidal rule that I put them inside this box. And here the second formula obtained using the Simpsons Rule that in general is supposed to be more accurate than the other one. So that's all for now. Thanks for watching.